It's important that to remember when dealing with trigonometric identities in terms of simplifying them or dealing with them in terms of equations, many times, actually almost all the time, there are really only two things that you're doing. You're either doing one, using some algebra, or two, you are actually using an identity. And what we mean by that is you have your identities memorized and you're replacing something that looks complicated with something a little bit simpler using an identity. So in order for you to do that, you basically have to have the identities memorized. So here are the reciprocal identities. We use the clue that these identities are the 1 over identities. So if you see 1 over, then that should be an indication to you that you are dealing with a reciprocal identity. So in other words, if I had, for example, 1 over cosine theta as an answer, then I could just say that 1 over cosine theta is one of these reciprocal identities. And here's how it's expressed here, that 1 over cosine is the same as the secant. So we can just replace it with the secant. So for our quotient identities, basically tangent is sine over cosine and cotangent is cosine over sine. All of our Pythagorean identities have squared on them. So every single one has a squared on them. So it's either squared or 1. So if we're trying to see if we're going to use a Pythagorean identity, look for some trig function squared and look for a 1 somewhere in that same expression. As an example, if I see 1 minus cosine squared theta, that makes me think of this identity. Or if I saw 1 minus sine squared theta, same identity. It's important to note as well that you can rearrange these. Sine squared theta plus cosine squared theta represents a relationship. It means that if we add these, that we're going to end up with 1. But of course, every addition problem, for example, if I said 2 plus 3 equals 5, can be rewritten to express the same relationship. I could say 5 minus 3 is 2, or 5 minus 2 is 3. All three of these express the same relationship between the numbers. So if I wanted to, if I subtracted, let's say I subtracted sine squared from both sides just to rewrite it, one way that I could rewrite it is I could say this relationship basically says that cosine squared is the same as 1 minus sine squared. Or if we did it the other way, we started with that same expression, and let's say we decide to subtract cosine squared theta from both sides. We're basically saying that sine squared theta is the same as 1 minus cosine squared theta. So remember that any of these identities can be rewritten to fit the problem. Cofunction identities are not that hard either. So for example, sine and cosine are cofunctions, or secant and cosecant are cofunctions, or cotangent and tangent are cofunctions. So in terms of our cofunctions, notice that they all have this pi over 2 minus theta on one side for an argument and theta for the other side. All that means is that if we take the two angles, so let's say we take this angle and add them together, what's going to happen? Well, theta plus negative theta is just 0. So that's going to give us just pi over 2 or 90 degrees. So in other words, as long as the two angles that we have here or here add up to 90 degrees, their cofunctions are equal. So just look out for this pi over 2 minus theta and recognize that you can replace it with its appropriate cofunction. So on our odd-even identities, we want to remember that really there are only two even identities. Cosine, excuse me, even functions. Cosine is an even function. That means that if we input a negative answer or if we input a positive answer, they're going to be exactly equal. Secant is also the only other even function because it's basically going to do the same thing. Notice what happens here on this row when we look at cosine and secant. So the reason why that happens is because they're even functions. With sine and the rest of our trigonometric functions, that's an odd function. So basically, if we input, let's say if we input sine of a certain value, and if we input sine of the opposite value, then the only way these are going to be equal is if we change it to the opposite. So basically, they're going to differ by this factor of negative. And this is just a generalization of how odd functions work. Going back to first semester when we talked about x cubed as an odd function, if we input, let's say, for example, -2 cubed, then that would be -8. But if we did 2 cubed, that would be +8. And the only way to make these two equal would be to make one of them the opposite number. So as an example, -2 cubed we said was -8, and 2 cubed was +8. If we wanted to make them equal, then we'd have to make the second one negative. So in other words, there's going to be a negative factor of -1 to make those equal. And that's really all it says. If we look at the first row and the last row, that's what we're dealing with. So as an example, if we did tangent of -30, that's the same as the negative tangent of +30. Or if we did sine of -45, that's the same value as the negative sine of normal 45 or +45 degrees. Again, we need to remember the two things that we are always going to do here is either one, we're going to use some kind of algebra, or two, we're going to use some kind of identity. So it's important, it's extremely important that we have our identities memorized. When you look at this problem, what's the first thing that you see? Well, if you have your identities memorized, then you'll probably focus in on this part. Anytime we have this expression here as an argument, pi/2 minus x, that means that we're using a cofunction identity. Remember that sine and cosine are cofunction identities. Also, cosecant and secant are cofunction identities. Tangent and cotangent are cofunction identities. So in looking at this, we know we can go between either sine and cosine, or secant or cosecant, or tangent or cotangent when we apply our cofunction identities. So what that means specifically for this problem is that we can replace the cosine of pi/2 minus x, that part, with just the sine of x. We're going to keep everything else the same. So we're still going to have that we're multiplying by the tangent of x, and we're still going to have that we're dividing by sine squared x. Now at this point, we remember some algebra. If we have, for example, u over u squared, we can basically divide both the numerator and denominator by u, since they have that in common. U divided by u is 1, and u squared divided by u is just going to be u. So if we apply the same thought process here with sine squared and sine, then you'll notice that we should be able to simplify this. So what's going to happen is that in the numerator, we're just going to be left with sine. Actually, let me correct that. We're dividing both the numerator and denominator by sine, so this sine is gone. And in the denominator, we're going to reduce out one of those sines as well. So what are we left with? We're left with just the tangent of x divided by the sine of x. Again, we're doing either algebra or identities. There's no identities that we see to apply here, so let's do some algebra. We think about how fractions work. That basically, if you have a division problem, it's basically a fraction problem. For example, if I have 10 divided by 2, that's the same thing as saying 10 times 1/2. Or if I have 15 divided by 3, that's the same as saying 15 times 1/3. So that means that we can take this problem and we can replace it with tangent of x times 1 over sine x. So again, we're either doing algebra, which we've clearly done, or we're using an identity. It doesn't look like there's too much more algebra that we can do, but we could replace the tangent with sine over cosine. So we can say that this is basically sine of x over cosine of x multiplied with 1 over sine x. And again, we're either using algebra or we're using an identity. I don't see any identities here, but what we can do is we can use some algebra. We remember that if we're multiplying, just how fractions work, 3 over 5 times 7 over 3 as an example, the 3's would eliminate, they would divide out, and then you'd be left with 7 over 5. If we use the same thought process here, the sine x would divide out with this sine x, and when you multiply everything together, you would just be left with 1 over cosine x. Remember that we're either using algebra or we're using an identity. When you look at 1 over cosine x, what identity do you think of? Well, we might think of a reciprocal identity, which says that 1 over cosine is basically the same as sine. So when we see 1 over cosine x, we're just going to call that sine x, and that's the end of the problem. So there's actually a small correction that I need to make. So first of all, where I have a sine of x, this is incorrect. 1 over cosine, according to the reciprocal identities, is going to be the same as secant of x. So here's another example. Pause the video and try and see if you can do this one yourself. Remember, there are two things that you're doing. Either you're using some algebra or you're using an identity. It's a good idea to check first if you can use an identity. When you look at this problem, do you see any identities? Yes, we see actually a Pythagorean identity here. So again, make sure you have your identities memorized. So what is sine squared plus cosine squared equal to? It'll be 1. So we can basically replace this portion here with just 1. What about the next part? It turns out that the next part is also equal to 1 if you have your identities memorized, but some of us might not see that right away. Remember that we know that the cotangent squared plus 1 equals the cosecant squared. So we can use some algebra to rewrite this equation. For example, what if we subtracted cotangent squared from both sides? Then we would just be left with 1 is the same as cosecant squared minus cotangent squared. So if we see cosecant squared minus cotangent squared, we can just replace it with 1. So we're going to take this expression and replace it with 1. So now we have 1 minus 1. So this is the easiest problem to figure out because basically this is what it's just going to be 0. Here's another problem you can try. Remember that what we're going to do here is either algebra or use an identity. We always want to try and see if there's some identity we can use first. Maybe that might simplify our work. So pause the video, think about if there are any identities that you see and what you would do. When I look at this problem, what I see is sine squared in the numerator. And it makes me think about an identity I have memorized, which is that sine squared plus cosine squared equals 1. So if we rewrote this, maybe by subtracted sine squared from both sides, then what would happen here? Well, on the left side, the sine squared would cancel out, and we'd have cosine squared is the same as 1 minus sine squared. So if I see 1 minus sine squared, I can replace it just with cosine squared. But notice that what we have here, 1 minus sine squared, it looks similar to the numerator, except that it's kind of switched around for the subtraction problem. So we're going to just use some basic math reasoning. A lot of this is just basic math reasoning. If we know, for example, that 5 minus 3 is 2, or that 4 minus 1 is 3, what would happen if we switch those values around the subtraction problem? So let's say 3 minus 5. We know that that's negative 2. Or 1 minus 4. We know that that's going to be negative 3. So clearly by switching the values around, we're going to end up with the negative or the opposite of the answer we normally would. So for our numerator, what that tells us is that instead of writing cosine squared x, we're going to write negative cosine squared x. Now what about the denominator? Well, when we see this negative x in here, it's a good indication that we're dealing with an odd or even identity. Remember that cosine is an even function. That means that if we put in a negative value or if we put in a positive value, that they're going to be exactly the same. So that means that we can take that cosine of negative x that we have here, this expression here, and just say that it's the same as cosine x. So we're going to replace it with cosine x. What happens when you divide a negative by a positive? You get a negative answer. What happens if you divide a square by the same value? For example, u squared divided by u, or x squared divided by x, or y squared divided by y. Well, clearly, you would just have one of those left over when you divide. So we're going to have just cosine left over when we divide cosine squared by cosine. So our final answer is this. We would have negative cosine of x. Here's another example to try. Please pause the video first, try and see if you can work it out, and then notice what we're going to do together. Now remember, either you're doing algebra or you're doing an identity. So when I looked at this, I noticed that there were no identities I could just get right away. There is an identity that has cosecant in it and cotangent, but it's a Pythagorean identity, and those are all squared. So the only thing I can think about doing right now is maybe doing some algebra. Now, this should be an automatic instinct. Every time you see what are called conjugates, so like a plus b and a minus b, those are conjugates. Or x plus 2 and x minus 2, those are conjugates. Or 2x plus 5 and 2x minus 5, those are conjugates. Anytime you multiply conjugates, it's going to be the difference of squares. That means take the first part, square it, take the last part, square it, and just make it a subtraction problem. So the second one, for example, would just be x squared minus 4. The third one would be the same thing. If you square 2x, what do you get? 2x squared is going to be 4x squared because it's 2x times 2x. 2 times 2 is 4, and x times x gives us x squared. If we square the negative 5, what are we going to get? 25. So 2x squared would give us 4x squared. 5 squared would give us 25. And then we would just stick a subtraction sign in between. You can check it yourself by foiling everything out, but that would be, again, a ridiculous waste of time. So we just need to know our algebra. Anytime you're multiplying conjugates, it's going to be the difference of squares. So let's see how we can apply it here. In the numerator, we have a value multiplied by its conjugate. If you notice, it's just like the other ones. They're the same, but they differ by either a plus or a minus in the middle. So when we multiply it, what are we going to end up with? Well, just like the other pattern, we're going to end up with cosecant squared minus cotangent squared. Of course, don't forget to put the argument so that y has to be there. And that's going to be over the cosecant. Just like in the other problem, cosecant squared minus cotangent squared is an identity. So we're either doing algebra or we're using an identity. So now, because we have them memorized, we remember that cotangent squared plus 1 is the same as the cosecant squared. So if we were to subtract the cotangent squared from both sides, what would happen? Well, the cotangent square would cancel out here, and then we would have just 1 on the left. And then we have cosecant squared y minus cotangent squared y. This expression is the same as 1. So when we work this problem out, we can say that our numerator would just work out to be 1. And we bring down what we already have, which is the cosecant. So we're either doing some algebra or we're using an identity. There's no more algebra to do, so what identity could we use? Well, we know that 1 over the cosecant is a reciprocal identity. So 1 over the cosecant, the reciprocal of cosecant, what is it? It's going to be the sine. So our final answer here is just the sine of y.